I write on the board with those. Okay, so pre-calc, section 4.3, trig extended circular functions. Hey, here's the deal. We are going to define our unit circle based on 45, 45, 90, 30, 60, 90 triangles. We will draw something we will refer to as a reference triangle to help us with our figures that we find, okay? But we're still using sine and cosecant, cosine and secant, tangent and cotangent, okay, across from each other because they're reciprocals of one another. We're still going to think about cofunctions because that'll help us find some answers when we kind of slow down and go, I don't know what I'm doing. So we can talk about that too. But really what we're looking at today is kind of a rehash of what we've done so far. Okay, you're going to see a little bit of everything today or tomorrow. I will be able to find trig functions of any angle, okay, find trig functions for real numbers, describe the periodicity of trig functions, and start my work on the unit circle. And you guys kind of started that a little bit on last night's homework, okay? Just to answer a couple things from last night's homework, the stuff that we're doing, thank you. Okay, the stuff that we're doing here, we talked about this yesterday. If this is 0, this is pi over 4, this is pi over 3, this is pi over 6. I was going to say pi over 2, but that's up here. This is pi over 6. And don't hold me to actually drawing it to scale because it's really not right now. But remember where those came from. I have 30, which is, by the way, pi over 6. 30 degrees and pi over 6 are the same angle. Okay, so this is a 30, 60, 90 triangle. Or I can talk about it as a 60, 30, 90 triangle. I know, beautifully drawn to scale. But across from 30, if this is 1 and my radius is 1, my hypotenuse, this is a half. This is the square root of 3 over 2. This is the square root of 3 over 2. This is a half. Okay, the reason why I'm talking about this is these are my coordinates, okay, to get to my spots on the circle. And I kind of talked about it yesterday. If I'm going out here, up here, okay, I have coordinates to get to pi over 6. Well, this is a 30, 60, 90 triangle, okay? Well, if I do that, this is 60. This is the square root of 3 over 2. This is 1/2. So coordinate-wise, this is square root of 3 over 2 and 1/2. I'm just using 30, 60, 90 triangle to help me find it, okay? If I'm looking at the 30, 60, 90 triangle still, up here, let's get a different color. Up here, this is my 60-degree angle, and this is my 30. And so across from the 60, remember, that's the square root of 3 over 2. Across from the 60, here, that's my y. Here, this is a half, square root of 3 over 2 to get there. And boy, that's slow, okay? Does that make sense? And I'm just using the function of my 30, 60, 90 triangle, my flipped one way or another to find those two coordinates. And this is x coordinate, y coordinate. That's how I'm getting there. Pi over 2, staying on the axis, but remember in the unit circle, we have a radius of 1. So if I go 0, 1, that's my coordinates here. And if I go 1, 0, that's my coordinates here. My last one is about a 45, 45, 90 triangle, okay? In a 45, 45, 90 triangle, remember, this is 1, this is the square root of 2 over 2. And this is also the square root of 2 over 2. We talked about that yesterday, okay? Well, those are my coordinates in a 45, 45 triangle. Okay, so those are the things we're going to be talking about today. I know that might be a little confusing, okay? But as we go through them, start kind of piecing those together because those are the coordinates we're going to be working with. Where did they come from? 30, 60, 90 triangle relationships, 45, 45, 90 triangle relationship, and the fact that we're using the hypotenuse as length 1, okay? And I'm just manipulating it in the first quadrant today. Any questions so far? We're okay? Now, let's talk about these functions. And I'll get rid of this stuff because it was just me going over some stuff. So we got trig functions of any angle. Okay, so we're talking about initial side, terminal side of rays. So if I got an initial side here of a ray, and I got a terminal side, and it goes that direction, keep in mind that's a positive angle measure, Okay, and I have an initial and a terminal. Identify the following using correct geometry notation. The initial side, well, I got a ray BC. The vertex is B. My terminal side, BA. Are you okay with those rays? I'll get that a little higher so you guys can see. Thanks, kiddo. Now, the measure of the angle is a number that describes the amount of rotation from the initial side to the terminal side of an angle. Okay, it's not shocking. Positive rotations are counterclockwise, and we've gone over that already. Negative rotations are clockwise. And we also have a standard position, or that we start with going to the side. You know, when we initially start with angles, if we talk about standard position, it's kind of, if we looked at the coordinate axis X and Y, it's pointing east, right? The initial side starts out east and goes around. If we think northwest, east, west, north, south, east, west. Yeah, that too. Okay. Just making sure everybody's got that down. And so standard position involves the placement of an angle on the XY plane so that the initial side is located in the positive x-axis and the vertex is at the origin. Okay. And I have my counterclockwise, 1, 2, 3, 4. That's really the big thing. That's why our standard position going counterclockwise positive is the way we number the axis. If you ever forget in this class, I always have students asking me, why in the world, Bloom, do you talk about the numbering from 1, 2, 3, 4 this way? I was like, we're in a math class. And it's how we talk about the coordinate grid. First quadrant, second quadrant, third quadrant, fourth quadrant. It's how our standard angle goes. So I get an opportunity to talk to students. They think I just am that absent-minded, but I kind of am, but there's always a method to my madness. Now in this next one here, we talk about negative. Well, the negative starts in the same position and goes around that way. Positive starts in the standard position and goes around that way. Are there any questions about those, just as a review? Okay, now how could two different angles have the same initial and terminal side? They'd be coterminal angles. Okay, and they would differ by multiples of rotations as we talk about them. And we talked about multiple rotations. We talked about coterminal angles, angles that end up in the same, their terminal ray is the same one. It's just that they could have more revolutions positive or just be the negative version of that angle. Coterminal angles do not have to have the same measure, be the same. You know, they don't have to have the same measure. Okay, they'd be different based on how they got there. And we've talked about that, so you guys have the visual of coterminals now. And we talked about coterminal angles with degrees, and we talked about coterminal angles in radians. We've also discussed that one revolution in degrees is 360, and one revolution in radians is 2 pi. So now all of a sudden this makes the most sense, at least way more sense than it would have been if I did notes like this on day one. Okay. Now, part of my notation, n is contained in the integer set, or the set of integers. That's what that means. That thing that looks like an E is a set notation for contained in, and Z is the set of all integers. Now, how can you find angle measure in coterminal angles? Maybe if I bring this up in degrees, wow. And notice the notation as we step through those. How can we find angle measures of coterminal angles? Just multiple revolutions in 360 or multiple revolutions in 2 pi. Okay, we can come back to the coterminal angle or the terminal ray when we started. And we knew that too now, right? So it's stuff that we've been doing and we did, and hopefully we're connecting the dots on them, you know, dotting the I's, crossing the T's on these. Are you okay with these, with the multiple revolutions? The first time that we would do this, if we didn't do those first 2 days, people will look at this, it's like, what are you talking about, Bloom? So I'm glad we went through those, that you guys were in the what were you talking about before we got to these notes, okay? Because we have a pretty good idea on what we're talking about there. Yeah. N and Z. And keep in mind, N's the number, this number is just representing a multiplier, and Z is the integers. So Z is the set of all integers. So everything going up to -2, -1, 0, 1, and 2, and beyond, but they're whole numbers and they're negative counterparts. Okay, and you got to think about it. I can have positive or negative rotations of 360 or 2 pi that come back to the same terminal ray. Does that make sense? For any one of the angles. So if I have a terminal ray here, and I have negative rotations, I could do a bunch of rotations coming around and coming back to the same ray. Okay, that's my negative version, so it's like -5 times 2 pi, or -5 times 360. But I could also do it in the positive direction and come up with multiple values of my terminal ray. You know, I mean coterminal angles that end at that terminal ray. Does that make sense? Okay, so that's where that N and Z come from, and Z is the set of all integers. Okay. And we went through the different sets on day 1 of notes first semester. So I'm just reusing some stuff that we had as we come through, but it's good to remind us. Okay. Now, any questions about coterminal angles right now? We're okay with that? Coterminal angles have the same terminal ray values, or same terminal ray, but probably different angles. Finding coterminals. Okay. I just want the positive and the negative version coterminal. So I've got this going on. If I'm going to go negative from here, going around, if I do the negative version, I've got that going on. And beta's -330. So 360 minus 30 will give me my negative coterminal. Okay. And then I can talk about this. If I want to go one more revolution, I can go 30 plus 360 gives me 390. Now, we also learned about reference angles, okay, in that first couple days. And a reference angle is the positive angle measure with the x-axis, and this is the closest x-axis, okay? And any reference angle of an angle in the first quadrant is the same. If I have 30, if I have 60, if I have 80, the reference angles would be according in the first quadrant. After that, they change, okay? Any questions? You guys do B, come up with a positive coterminal, and a negative coterminal of -150. This wants one of each. Okay, so you get that. You're just doing one more revolution or multiple revolutions in one way or the other. And if you need, have a calculator. It's -150 plus 360, -150 minus 360. And that's all I did. -160 or 150 plus 360 and -150 minus 360. That's how I got the 2. Are you okay with those? I'm just going one full revolution away, okay? And one full revolution in degrees is 360. And I have the positive version and the negative version. Now, in terms of radians, a full revolution's 2 pi, okay? In terms of radians, I have to work with fractions. I know, I said the F word in class. I know, it's scary. Okay, fractions are the boogeyman in mathematics. Okay, it's the thing that's under the bed that's going to scare you when you're sleeping. Okay, I hope it's not. I hope we can start getting more friendly with that. Fractions are friends, okay, not the boogeyman. So when we're looking at this, I got 2 pi over 3 radians. Now remember, full revolutions in terms of 3, okay, I've got 2 pi over 3, but full revolutions in terms of 3 has to be 6 pi over 3, because 6 divided by 3 is 2. So I'm going to add 6 pi over 3 and subtract 6 pi over 3 to get the 2. Does that make sense? One revolution, remember, is 2 pi. 6 pi over 3 is the same as 2 pi. So I'm going to add 6 pi over 3. Why is that? Because I am dividing by 3 in this particular angle that I'm provided. In order to find the coterminals, one positive and one negative, I am going to add or subtract 6 pi over 3. If I subtract 6 pi over 3, I should get negative 4 pi over 3. Does that make sense? If I add 6 pi over 3, I should get 8 pi over 3. One full revolution away. But I have to know what form I'm going to be working with, whether it's radian or degree. If it's degrees, full revolution is 360. If it's radian, full revolution is 2 pi. Okay, and pay attention if it's in fraction, you got to have it in fraction form so you can easily work with it. Any questions about those? Doing okay? Yes, sir. Who do you need? Oh, that, yeah, yep. Chandler was trying to get everybody to clap, so let's clap for Chandler. Yay! Maddie, yay! Round of applause. Or you can go 2 pi revolution if you'd like. Yeah, no, we're all good. We're all good. Colas is kind of shy. Oh, ooh. Thank you, sir. Well, don't you guys look great with your flowers? That's great. Okay. All right. So here's the deal. We're looking at this quadrant thing. Talked about what do I got to do to get to quadrant 1, quadrant 2, quadrant 3, quadrant 4. And that's just the positive or negative value of my x and y. Okay? You all right with that? And plus plus, minus plus, minus minus, plus minus. We need to extend our trig functions so they can apply to any angle. We will start in the first quadrant. And what I want you to be thinking about this reference triangle. Okay? Now get out of the way, put that one down. Let's think about that reference triangle in itself. And so we're going to use the acute angle definition of the sine function. And people are wondering, how in the world did I come up with this reference triangle? First, in this investigation, this exploration, they told me we're in quadrant 1. Okay, that's how I oriented my triangle. So it's in quadrant 1. They told me that the points P are x, y, all right, in my coordinates. That's where I was able to find that my x coordinate was x and my y coordinate was y. And people are like, ooh, good, Bloom, you're just like Captain Obvious today, all right? It's too bad today's not superhero day. Captain Obvious. Hoodie, that's what you're wearing, right? Okay, I'm just kidding. Yeah, you got it going. Yeah, so you got your hoodie on. All right, Captain Obvious is going. And then they talk about the fact that r is the distance from P to the origin. That's where I got r. All right, are you okay with the orientation of my reference triangle we're going to use? Okay, x being the x value, y being the y value, r being my radius of my circle that we've seen, but it is my hypotenuse. Okay. Now, if I'm talking about how I define sine, they say, hey, use the acute angle definition of sine function to prove that sine is theta over y over r, y over r, excuse me. All I'm doing is, hey, they defined it as opposite over hypotenuse. Well, the opposite, the theta, is y. The hypotenuse is r. That's how I know that that is true. Okay, that's all I'm doing. And people are like, well, Bloom, come on. I mean, that's the y value and r. Why r for the hypotenuse? Think about what we were talking about earlier with the unit circle. The hypotenuse masquerades as the radius of that circle. Okay, so we're learning about the connection between sine, cosine, and tangent and what will suit for our future will be on the unit circle, and r being hypotenuse. And in the unit circle, it's always 1. Okay, so cosine theta adjacent over hypotenuse is x over r, and the tangent is opposite over hypotenuse, was y over x. Are you okay with how I'm using this? And this is the way they defined them, and that's why I was such a crazy guy about using opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent to get it done. Okay. Now, in question 3, they talked, 2 and 3 we covered. In 4, express the remaining 3 basic trig functions in terms of x, y, and r. Well, I have cosecant. What's going to be cosecant? The flip, right? Cosecant is 1 over sine, so it should be r over y. Okay. The secant, which is 1 over cosine, should be r over x. And the cotangent, as we look through these, if I can bring these up, I have them over here someplace. They're disappeared. So we're going to talk about this way. When I'm talking about the sine, I've got cosecant of theta. Okay, it's hypotenuse over opposite. I've got the secant of theta, which is 1 over cosine, which is going to be hypotenuse over adjacent. Somebody can't put his J across. And then my tangent was cotangent of theta, which is my adjacent over opposite. And these values should come through. Okay, good. That's where I put those. I'm just going to get rid of those. And it should have been r over y. It should have been r over x. That's what they should have been equal to. And this should have been x over y. Are you okay with those connections? Now, keep in mind, in the unit circle, r would become 1. Okay, so when I look at the sine, if r is 1, what's my answer? Y. If I look at the cosine, if r is 1, what's my answer? X. So I'm saying right now, I'm going to define my cosine of theta to be my x value in my unit circle. I'm saying my sine of theta is going to be my y value in the unit circle because r is 1 in that case. Okay, so that's what we're going to be working on. And that's why the unit circle is all about the radius, or in our case, when we were working with the special right triangles, the radius or hypotenuse being 1. So now my next question, and maybe I should just get rid of this so you guys can see what I'm doing. Or okay, I want you to look at my reference triangle that I put in. Okay, I have a reference triangle. Let theta be the acute angle in standard position whose terminal side contains the point 5, 3. Okay, find the 6 trig functions of theta. But remember, I'm evaluating this in quadrant 1. They tell me you're going to set this up in quadrant 1. So in order to do that, I have my quadrant 1. Where did I get 5? Right there. Where did I get 3? Right there. Okay. Are you okay that my point P out there is now 5, 3? Could I find, in this particular case, we're not working with the unit circle yet, so could I find my radius length, or better yet, my hypotenuse? Do you have a skill set to allow you to find the hypotenuse? So 5 squared plus 3 squared, okay? 25 plus 9 is square root of 34, and we have a timeout. Yay, Gabby, yay. Yeah, and, oh, we got 2 more. Oh, darn. Okay, thanks for coming in. All right, so are we okay with the things I've done so far? Yes or no? Does it make sense why I chose it to be in the first quadrant? Does it make sense where 5 and 3 came from? Does it further make sense why I'm finding the hypotenuse? 5 squared, 3 squared. Let's just talk about it. I'm going to use Pythagorean theorem to find my r. My r is equal to the square root of 5 squared plus 3 squared. He lied. Oh, somebody else. What do you have, miss?
This one, sorry.
Who?
Grace Jacobs and
Bixby? Whoop.
sorry.
Flower down, flower down. And Jacobs, where are you sitting? Gracie? There you are, dear. And Bix. There you are, dear. Okay, so are you okay with the fact that we have 25 and 9, which is the square root of 34? Yes or no? Okay, so I should have the square root of 34 up here as my hypotenuse. Now I just want you to find, based on y to r, x to r, y to x, you're still doing the same thing. I just want you to start seeing that your sine is y over r. Your cosine's x over r, okay? Because those are big, because sine and cosine are y and x respectively. Okay, so find your answers. Go. And I use a reference triangle to help me based on the information they provided to me. They told me we were in quadrant 1. They told me the coordinates of the point I'm concerned with were 5, 3. 5 being my x horizontal value, 3 being my y vertical value. And then I was able to find my hypotenuse based on that. So fill in the remainder. Okay, so we should have these going on. I made them all nice and pretty as I went. Are you doing okay? Remember, this is about ratios. It's about us finding the ratio of a particular angle based on a reference triangle. Are there any questions regarding that? Okay. Now, use the same definition of x, y, and r, whether or not x and y are positive, and you can extend the trig functions to any angle. So why will r always be positive? R is the distance from the origin to the point P. Okay, so r is always going to be a positive value. But depending on what quadrant I'm in, that's going to change. Okay, if I'm in quadrant 2, my x is going to be negative, my y positive. If I'm in quadrant 3, both of them are negative. And then I'm in quadrant 4, they're both, well, one's positive and one's negative. So you have to orient yourself with that as you're thinking about the problem. So in problem 3, I'm not in quadrant 1. I'm at negative 5, 3. So go ahead, see what you got with that information and see what you can find. Okay, and once again, did you notice that my hypotenuse is the square root of 34 again? Okay, so go ahead. I'm just changing the orientation of the quadrant and consequently my reference triangle. Okay, so sine, still y over r, but think about my sine value. Now, I want you to emphasize this, that when I'm looking at the sine of theta, it goes up from the axis, right? So it should be positive. When I'm looking at cosine of theta, it's going to the left from the origin, so it should be negative. Okay, are you all right with the orientation and the sine value? Okay, tangent is a positive divided by a negative in this case. So I'm looking at the idea that it should be negative itself. Are there any questions on those? And then reciprocals, they'll just go pretty quick. I just got to make them all pretty if I need to and get that going on. We're doing all right. Okay, making sense? Any follow-ups with anything that you're wondering about? Now, remember, there are an infinite number of coterminal angles that have the same 6 trig functions. I just do another revolution, I'm back at that same one, whether positive or negative. We talked about x, we talked about y, we talked about finding that point, we've talked about positive angles coming out there. So in definition of our trig function of any angle, let theta be in any angle in standard position, be any point in the terminal side of the angle except the origin, okay? And let r denote the distance from P to the origin, and then we have r, which is our Pythagorean theorem, right? And we've done that already. We've kind of walked through it, and these are the things we've already done. Y over r, x over r, y over x, r over y, r over x, and x over y. They're reciprocals of each other. What happens when we are not given a point P to begin with? Okay, you can use a 45-45 or 30-60 because they will probably give you an angle. Okay, are there any questions about that? Let's see what we've got here. Did I just skip? Which one are you talking about? This? I'm going to have that up there. It'll be there. Now, I'm going to let this roll. I got a 315-degree angle. Okay, I made my axis. I put it 315 degrees in. It's positive. I end up here. I have my reference angle here, which is 45 degrees. Are you okay with my reference angle? Okay, remember, after I get the 315, I have a 45-degree reference angle. It's 45 degrees more to get to the axis, okay, of where I started. But the reference angle is going to help me find my values I need, okay? They should have the same sine, cosine, and tangent. Are you okay with 360 minus 315 gives me my 45? And then I got a 45, 45, 90 triangle. So when I did that, I have that square root of 2 as my hypotenuse. And remember, we're not working with the unit circle yet, so I can have a radius, or in this case, my hypotenuse length, greater than 1. Based on that 315, I'm going to use my relationships of y to r, x to r, y to x to find my sine, cosine, and tangent, and then use the reciprocal properties, because the reciprocal of sine is cosecant. The reciprocal of cosine is secant. The reciprocal of tangent is cotangent, to find my other properties. Go ahead, give it a pop. It's your turn. This is a you do. This is a you do. Now again, any questions on how I set anything up with my reference stuff? I know it might look like a secret, but normally when I'm writing it up, I'm blocking somebody, so I wanted to put it up before I got to the problem. Are you okay with what I did? With my angle, the fact it was positive? You okay with where I place my terminal ray? You all right with the reference angle I'm using? Okay, that's setting up my reference triangle. Notice the reference angle sets up my reference triangle. There's a 45, 45, and now I'm going after my ratios. And I make them pretty. Once I get them done, reciprocals of those ratios, help me with those. Any clarification questions? Now, the reason why I was worried, I was just making sure I'm at the right spot to be almost, a comfortable timing for notes to make sure I'm asking questions and getting that done and not rushing you on the next days. And we have plenty of time the next 2 days to finish our notes. I know Friday we have a shortened hour. By the way, who's going to be involved Friday to the point that they need to leave fifth hour? I mean, it's before lunch because of our numbers. I think we're going to go to lunch first, maybe. I don't know. It's going to be funky. We'll see. Maybe it'll be okay. I think we're going to go 1, 2, 3, 5, 4, 6. I think that'll be the order of the day. So fifth hour we should be okay. Sixth hour has always been an issue, so we should be all in there. I don't think anybody's going to miss. If you are, talk to me about what's going on, and I'll make sure that we videotape what's happening. Okay. Questions about these? Is it making sense? Okay, cool. And then let's see where we're going to go. Let's do this, and then we'll talk about this tomorrow. Okay, so this is where we're going to end up today. You have today's assignment. That's at the end here. We're going to get there. So that's up. 4-3 day 1. That's going to be getting going. It's also a thing on the board. It's also what's online, so you know what's going on. Thanks for your time today, and have a wonderful day.